Hello friends, I welcome you in lecture number 2 on higher order partial differential equations. In previous lecture we have taken brief introduction about linear partial differential equations with constant coefficients, and we have seen that there are two types of linear PDEs with constant coefficients, homogeneous and non-homogeneous. And we have also understood that we can write linear partial differential equation with constant coefficients in this form: function of d and d dash z equal to 0, where this capital F is a function of d and d dash. D stands for partial derivative with respect to x, d dash stands for partial derivative with respect to y. And we have also discussed that this capital F can be a homogeneous function of d and d dash, or it can be a non-homogeneous function in d and d dash. Now first we are going to discuss the methods for solving this homogeneous linear partial differential equation with constant coefficients, in which this capital F is a homogeneous function of d and d dash. First we will discuss that how to solve this type of linear PDE with constant coefficients, in which this capital F is a homogeneous function of d and d dash. And then we will go for non-homogeneous linear PDEs with constant coefficients, and then we will also discuss that how to solve the linear PDEs with constant coefficients, in which this capital F is a non-homogeneous function of d and d dash. We understand the method first with the help of example, and then we will generalize it for linear PDEs with any order. Here I have taken this linear partial differential equation of second order. You can see all the coefficients are constant, and we can rewrite this in terms of d and d dash. Here we have second order partial derivative with respect to x, so I am writing d square. Then here I have both the partial derivatives, partial derivative with respect to x, partial derivative with respect to y, and here I have second order partial derivative with respect to z. And we can see here right hand side is 0, that is this is linear partial differential equation with constant coefficients which is homogeneous. And here our function f, capital F, is homogeneous in d and d dash. We can see that in each term degree is same. Here degree is 2, here also degree is 2, and here also degree is 2. Therefore capital F is a homogeneous function of d and d dash. So what we are discussing? We are discussing the method for solving linear partial differential equation with constant coefficients which is homogeneous, and in which this capital F is also homogeneous function of d and d dash. So first step is we have to write down the auxiliary equation for this given equation. Suppose I give this number 1, then first I have to write down the auxiliary equation corresponding to given equation. So for that we remember that we will replace partial derivative of x with respect to x by, say, small m. Replace capital D by small m, and d dash will be replaced by 1 in function of d and d dash, and equate to 0. Replace capital D by small m, d dash by 1 in capital F, which is f of d dash, and equate to 0. Here f of d dash is 2d square plus 5d dash plus 2d dash square. So if I replace d by m, here I will have 2 into m square, plus d is replaced by m, here I will write m, d dash is replaced by 1, plus 2, d dash is replaced by 1 and equate this to 0. So after doing this, we will obtain quadratic equation here. This is equation of degree 2 in variable m. So because our equation is of second order partial differential equation, we obtain second degree polynomial in variable m. Suppose our partial differential equation is of order 3, then we will obtain third degree polynomial in variable m. In general, if we have nth order linear partial differential equation with constant coefficients, then we will obtain polynomial of degree n in variable m. And we know that if we have second degree polynomial, we have two roots or two values of this small m satisfying this equation. So first step is to write down the auxiliary equation and then solve that auxiliary equation. So this we can easily solve. We can rewrite 5m by 4m plus m and plus 2 equal to 0. Here I can take 2m common and here I am left with m plus 2. Here I can take 1 common and I will have m plus 2 equal to 0. Again I can take m plus 2 common, therefore m plus 2 times 2m plus 1 equal to, therefore we have two possible values of m. We can see that this product is 0 if m plus 2 equal to 0 or 2m plus 1 equal to 0. Therefore we obtain two values of m satisfying auxiliary equation, m equal to minus 2, and from this I will obtain m equal to minus 1 by 2. And we can observe that these two values of m are different or distinct. That is, we have distinct roots for our auxiliary equation, which we have obtained by replacing d by m and d dash by 1 in f of d comma d dash and equating to 0. So whenever we have distinct roots for auxiliary equation, then remember this standard form of general solution. We are having ready-made formula for the general solution. In each case we have two cases, roots are distinct and roots are equal or repeated. Therefore the general solution of given equation is, in given equation dependent variable is z and independent variables are x and y. So remember this form in the general solution: some function of y plus m into x. We are going to write this type of functions in the general solution for each value of m, which is a root of auxiliary equation. Here I have two values of m satisfying auxiliary equation, so I will write two functions of this type corresponding to each value of small m. So for m equal to minus 2, I will put m equal to minus 2 here, and I have function of y minus 2x, and this function I denote by phi 1. Similarly, I have to write another function for m equal to minus 2. So here I put m equal to minus 1 by 2, and I will have y minus 1 by 2x, and this phi 1 and phi 2 are arbitrary functions. We can rewrite this, therefore I keep this as it is: phi 1 of y minus 2x plus this I can rewrite as, if I take this 2 in the multiplication of y, I can rewrite this as 2y minus x divided by 2, and therefore we can rewrite our general solution as z equal to phi 1 of y minus x plus some another function, say psi 2 of 2y minus x, where this psi 2 function is nothing but this phi 2 of 2y minus x divided by 2. We can ignore this constant, and here variable is 2y minus x. So we have function of 2y minus x here. Here we have function of y minus 2x. And this phi 1 and phi 2, we have to mention that they are arbitrary functions. Phi 1 and phi 2 are arbitrary functions, and this is the general solution of given homogeneous linear partial differential equation with constant coefficients, in which we have this capital F is homogeneous in D and D dash. So this is first case. In case of distinct roots, we will have ready-made formula for the general solution, and that formula contains functions of this type: arbitrary function of y plus m into x, where m is a root of auxiliary equation which we obtain by replacing capital D by small m and d dash by 1 in capital F of d dash and equate it to 0. I have taken another example in which I will obtain repeated roots. So first I write this equation in the form of d and d dash. This I can rewrite as d square plus d dash square plus 2 times d and d dash z equal to 0. And first I have to write down the auxiliary equation. Now we can directly write down auxiliary equation. What we have to do is consider capital D equal to small m, d dash equal to 1. So I have m square plus 1 plus 2m and equate it to 0. That is, I have m square plus 2m plus 1 equal to 0. Therefore, this I can rewrite as square of m plus 1 equal to 0. Therefore, m has minus 1, that is repeated roots. We have the case of repeated roots now. So therefore, what will be the formula for general solution? So if you recall, in the case of ordinary differential equations, if we have repeated roots, then we multiply by powers of independent variable x. So that is same thing here. First, for m equal to minus 1, I will write arbitrary function of y plus mx. M is minus 1, that is y minus x. Second root is also minus 1, so I have to write another function of y minus x, but these two are same. So here these two are not independent, so to make them independent, I will multiply this function by x. So whenever we have repeated roots, we will be multiplying by powers of x. If we have 2 repeated roots, we are going up to single power of x. If we have 3 repeated roots, we will add one more term as say x square times phi 3 of y minus x. So the theory is exactly same as in the case of linear ordinary differential equations with constant coefficients. And here this phi 1 and phi 2 are arbitrary functions that we have to mention. So what we have discussed is we have homogeneous linear partial differential equation with constant coefficients, and in which capital F d dash is a homogeneous function of d and d dash. In general, I have written the method here. Suppose I am considering partial differential equation of nth order, then I am starting with nth order partial derivative of z with respect to x n times, then del raised to n z by del x raised to n minus 1 del y, n minus 1 times derivative with respect to x and single time derivative with respect to y. and I am considering the case that this capital F becomes a function of d and d dash. Therefore, I have taken care that in each term order of derivative is n, because recently we are discussing the method in which this capital F d d dash is a homogeneous function of d and d dash. So this is the general form of those type of equations, and right hand side is 0, that means it is homogeneous. Now using these notations, that is partial derivative with respect to x is d, partial derivative with respect to y is d dash, we are writing this equation in terms of d and d dash. Here I have partial derivative with respect to x n times, so we will write d raised to n z here. Similarly, plus k1, partial derivative of x is n minus 1 times, and single time partial derivative with respect to y, that is d raised to n minus 1 d dash z, then k2 d raised to n minus 2 d dash square z, and so on. Last term is kn d dash to the power n z equal to 0, and by taking z common we will have this form d raised to n plus k1 d raised to n minus 1 d dash, and so on, kn d dash raised to n z equal to 0, and this is nothing but capital F, which is a function of d and d dash, and we can see in each term degree is n, therefore this is homogeneous function of d and d dash. And to solve this equation number 1 or equation number 2, which is written in another form, we have to first write down the auxiliary equation. For that we will replace d by m and d dash by 1 in this f of d d dash, and we will equate it to 0, and we will obtain this auxiliary equation. This is a nth degree polynomial in variable m, and therefore it has n roots because it is of nth degree. Suppose n roots are m1, m2 up to mn. So here I have written this equation 3 is an auxiliary equation of given equation, and it has n roots. Suppose these n roots are m1, m2, mn, and depending upon the type of these roots we have ready-made formulas for the general solutions. And here I have written two cases. First case is all the roots are distinct, that is m1, m2 and so on, mn are all distinct, and in this case the general solution is given by z equal to arbitrary function of y plus m1x plus arbitrary function of y plus m2x and so on, nth arbitrary function of y plus mnx. All we have to remember is that we are considering the addition of arbitrary functions of y plus mx, and here values of m are n, so we are writing n arbitrary functions by considering m equal to m1, m2 up to mn, and this is the formula for general solution in the case of distinct roots. Now if roots are repeated, suppose we have k roots are equal, out of these n roots k roots are equal and remaining roots are distinct, then general solution is given by this formula. We have k equal roots. Suppose all roots are denoted by small m, then here I have written y plus m1x, so m1 is equal to m, so I am writing m here also, up to mk, all roots are equal to m. So to make them distinct or independent, here I have multiplied by x, here I have multiplied by x square. If I have 3 equal roots, I have to go up to x square. So if I have k equal roots, I have to go up to x to the power k minus 1, and remaining roots are distinct, so that I have written here. mk plus 1x, mk plus 2x, and so on. And this phi1, phi2, phi-n are arbitrary functions. So remember this method, what we have discussed? We have discussed homogeneous linear partial differential equation with constant coefficients, in which this capital F is also homogeneous function of d and d dash, homogeneous function of d and d dash. So in that case, first we have to write down the auxiliary equation. For that we replace d by m, d dash by 1 and equate to 0, and we will have polynomial in variable m. Then we will solve that polynomial, and depending upon the nature of roots of that polynomial, we have different formulas for the general solution. And in those formulas, what we are writing? We are writing arbitrary functions of y plus mx, where m is a root of auxiliary equation. So we will discuss some more problems of this method in upcoming lectures. Thanks for watching.